Simulation is a broad topic that can add a lot of value across the design, implementation and operational phases of your project lifecycle. In its most simple form, simulation is a test bench, allowing you to test your process, automation or plant digitally before you develop the physical solution.
Firstly, why are we talking to you about simulation? Simulation can support you with challenges that arise from constant pressure to produce with a quicker time to market, more flexibly and more efficiently, whilst not compromising on plant safety or quality. Quite often without the ability to go out into the labour market and just hire more people. To do this, we need to look beyond the traditional approaches to design, engineering and operations, and introduce new technology such as simulation to achieve these goals. As we will discuss, simulation is able to address these challenges in a number of ways, be it reducing time to market by supporting digital first plant design and virtual commissioning, improving efficiency with a live digital twin, or supporting skills gaps with operator training systems. So before we go into detail on this, what do we mean by simulation? And how do we get started? In short, by utilizing simulation tools, you are combining the real and the digital worlds and becoming able to more effectively design, test, optimize, and learn how to operate your production facility without having to interact with the physical system. Simulation is a very broad topic with many different solutions and use cases. It is one where often asking the right question is as important as finding the right answer. And the key question really is, where is the best place to maximize value? This will depend on where you are in your automation journey. Are you looking to build a new plant and want to optimize your plant layout ahead of time? Or are you a brownfield site chasing increased efficiency? And at what level of the plant hierarchy are you focusing on? Are you looking at an individual machine you would like to optimize? Or would a global model of the system allow you to better understand the impact on changes in one area on your wider process? And finally, what kind of simulation are you looking for? Would you derive the most value from better understanding your process? Or how your automation system operates? Or how the physical plant is operating? All these questions are relevant, and Siemens can support you in better understanding where this value may lay and how to start on your simulation journey. In this slide, we have condensed down some of the key use cases we see for simulation, focusing on the end-to-end life cycle of a process production facility. Starting at conceptual and process design stage, we at Siemens have solutions for process modelling using our GPROMS platform. This utilizes detailed mechanistic models of chemical processes to support the design and upfront optimization of production facilities by creating a one-to-one digital representation of the process. This flowsheet can be produced at an individual unit procedure or full process level by utilizing GPROMS global modeling capability. This process model can then be supplemented by real lab data to predict the design parameters required for full production scale, up without the need for intermediate physical lab scale pilots. Through into the engineering and commissioning phase, we can perform virtual commissioning of our automation code using our automation digital twin platform, SIMIT. SIMIT creates a replica of our physical plant that the automation system would interact with and allows us to test our automation code as it is being developed, reducing the reliance of physical commissioning where any bug fixes or issues are significantly more costly. Finally, in the operation and modernization phase, we can utilize this SIMIT model alongside our automation system to train operators in a risk-free environment. By utilizing this system, we have been able to demonstrate with customers an up to 8% reduction in operator mistakes. We can also use the process model we built alongside our SIMIT and automation system to begin to do online optimization of our production by using additional soft sensing and model predictive control and operator next best actions. Of course, going forward, once it comes to updating the plant, we can firstly validate proposed changes virtually before risking changes to the physical system. So there is a lot of value across the whole of the plant lifecycle, but it's really important to note that maximum value comes from utilizing these tools from the start to the end. So it is beneficial to really buy into and use these tools from the start. Here is a quick summary of some of the use cases we just discussed. Maximum decision-making safety thanks to improved engineering and automation quality, faster commissioning with fewer risks, increased plant availability and safety and optimized production.
Thank you for joining me as I introduced the topic of simulation, explored the value and defined where it can be used. In the next video, I'll go into detail on one of our solutions for the automation digital twin, which is SIMIT. In this video, we're focusing on SIMIT, our automation digital twin, which can be used to test your automation code during development, allowing you to find errors or bugs earlier and avoiding costly fixes during the physical commissioning phase.
SIMIT, in simple terms, is replacing the real world with a virtual equivalent. At the top level, we are keeping the means of the operator to interact with the control system, but then we can replace everything below this. The PLC or AS remote I/O, actuators and sensors, and finally the plant/machine. And as far as the control system is concerned, it is talking to physical plant, but instead, it is all virtual. As with all of these solutions, SIMIT is modular and can be deployed at 3 levels, depending on where the most value will come from. Firstly, at the signal level. Here we are simulating the PLC or AS and the remote I/O stations using the SIMIT virtual controller. We are able to receive signals from the control systems, force values, and emulate the behavior of the physical hardware. This is great for simple tests, but doesn't provide realistic feedback to our control system that would be received from the physical actuators and sensors. This is where the second level comes in, device level. We are now starting to build simulation models in the SIMIT simulation platform. Utilizing the inbuilt libraries of SIMIT, we can build medium fidelity simulations of individual devices such as valves, pumps, and motors, providing more realistic feedback to the control system for more advanced testing. To make this process efficient, we can use templates matching those in the control system, and even do mass instantiation to build the device-level simulation of the full plant in a few clicks. This is really useful for testing individual devices, but what if we wanted to test how our process is working overall, by stepping through a sequence? This is the third layer, process level. Using SIMIT libraries, we can now build up P and ID style networks using general unit procedure level models or more industry-specific models, with add-on libraries, for example, life sciences and water. Finally, SIMIT has a concept called a coupling. This is the means of exchange of data between SIMIT and the outside world. For example, the virtual controller mentioned before is a coupling. There are other couplings available for connection to non-Siemens automation equipment via OPC UA, and also to co-simulation tools such as SIMIT or NXMCD. SIMIT can be seen as the center of a wider simulation solution. An additional benefit of SIMIT using a virtual controller is the ability to speed up and slow down simulations, increasing productivity and acceptance testing. To summarize, SIMIT is here to make virtual production real, be it at the signal, device, or process level, increasing sophistication of your simulation model and adding value as you do. And conceptually, the easiest way of thinking about it is you are just flicking a switch. Instead of the physical plant, you are providing a virtual equivalent with the ability to connect through to co-simulation tools such as GPROMs.
Thank you for joining me in exploring the value that automation digital twins can bring during development and carrying through that value into the operations. So we've explored the value of simulation and taken a deeper dive into our automation digital twin, SIMIT. Let's look at how we've implemented this in the real world with an example from one of our solution partners.
I will be going through 2 examples which between them will really highlight 3 areas where simulation is already adding value to our customers. As we have discussed in the previous video a lot about virtual commissioning, we will be focusing on operations and modernization. The first is with Linde in Germany, which amongst other things is a large global process gas supplier. This example is for a virtual training solution running alongside one of their high-CO plants. The plant was utilizing SIMATIC PCS7 as its distributed control system platform. There was a requirement to find a way of training plant operators on a number of scenarios in a realistic but controlled plant environment. The system needed to always be available when it was needed, it needed to be flexible to adapt to plant changes and training scenarios, and ultimately needed to be commercially viable. Linde decided to use SIMIT simulation platform to achieve this task. By creating a digital model of the automation within SIMIT, operators were able to use the PCS7 operator interface to train on different plant scenarios, knowing that there would be no consequences to the physical plant if mistakes were made. The second case is with SABIC. Working with the ethylene cracking furnace, these systems are handling material at scale, so system availability is crucial, and any improvements in efficiency will result in large cost savings for the process. Specifically, SABIC were having challenges in predicting the impact of cooking rate on overall plant yield, and therefore couldn't define the optimal operating mode for the plant. To address this, Siemens deployed our process modeling platform GPROMs. Within GPROMs, we have G-Process, which includes the ability to high-fidelity mechanistic models and soft sensing using libraries specifically designed for the process industries. SABIC were able to predict yield based on operating conditions in real time, run length predictions, what-if analysis, as well as condition monitoring. This digital model was then turned into a full real-time digital twin by closing the loop between the physical plant and the digital model, using real-time feedback and advanced process control, allowing real-time optimization of the plant. The impact of this solution for SABIC was enormous, resulting in a total of $10 million a year in savings.
That's all for simulation. Simulation is a very broad topic where the right question is often as important as the right answer. There's value to be found across disciplines from process, automation and physical twins, as well as all the way across the project lifecycle. We're focused on automation here, but if you want to learn more about Siemens' holistic solutions to simulation, scan the QR code to find out more.